Welcome everyone to another session of the data learning seminars. Today we have Marius Wiggert from the University of Berkeley. He did his PEA in the TUM. Then he did a couple of roles in the World Fund and Mackenzie as well, and currently is a postdoc at UC Berkeley as well. Thank you, Marius, for sharing your work with us, and I'll leave the audience with you.
Thank you, Kazar. And yeah, welcome everybody. Thanks for your interest in showing up. In this talk, basically, I'll summarize most of the big chunk of my PhD work, and it's about tackling climate change with autonomous seaweed farms, hitchhiking, and ocean currents. And basically, questions rather towards the end, like I'm going to go through various techniques we developed in various areas, and we can happy to drill into the details later on in the questions. I'll leave some time for that. All right, the research we do is motivated by climate change. And basically the idea is that to prevent the worst tipping points that would trigger runaway greenhouse gas effects and cause more extreme weather events, we need to stabilize the temperature increase to 1.5 degrees. And according to the IPCC, we need to do two things to make that happen. One is reducing emissions, basically getting down this curve to as much as we possible by transitioning to zero emission technologies like renewable energies, stuff like that. And there's a second thing we need to do. Currently, it's not that much we need to do, but basically it needs to scale up soon. It's the carbon removal. And we need to scale up carbon removal to 2 to 10 gigatons per year in the 2050s. And that's a lot. Gigaton is 1 billion tons. And currently we don't have much technologies to do that. And for carbon removal, what I will propose to you or suggest to you is that seaweed can be a surprising ally for that. Because seaweed, on one hand, it provides food and shelter for countless marine animals, but it also grows incredibly fast. And it can double the biomass each week. So you have a very nice exponential for quite long, and then it flattens out, like in a sigmoidal shape. And basically how it works, it grows near shore. Basically, it takes up via photosynthesis CO2, just like every other plant. Marine photosynthesis is a lot more effective. That's why efficient. That's why it can grow a lot faster. And when it dies, part of the biomass actually gets fractured and makes its way to the deep ocean. That already happens naturally. And if it gets below 1,000-meter depth, below the thermocline, the biomass that makes it down there, the carbon which is contained in that biomass, is basically out of the atmosphere for thousands of years. And that effect already currently removes about 100 to 200 megatons, million tons per year, and naturally. And the idea is now, what if we can scale this process to the vast areas of the open ocean? And the question is, how can we do that? And one idea is very natural, is we know how to do seaweed farming, so why don't we scale nearshore seaweed farming? The issue is the transport to the open ocean, to the deep ocean, is actually quite costly because you need to get all that mass, you need to transport it all the way over, which also has embodied emission again. So not that great. Another one is why don't we just anchor in deep oceans in 1,000-meter depth and then just sink it there, and we don't have to transport it. The problem is that anchoring in depth is very expensive. We can do it for oil platforms, but basically because of the length of cord and the forces it has to hold, the costs increase exponentially with the depth you want to anchor in. So also not ideal. So that's where the idea from the startup I work with, FICOS, comes in, is why don't we build floating farms? They're basically just little boats. I think the top is a sketch version. I'll show you a photo of the prototype later on. But why don't we build floating farms which have a net where they grow seaweed on the bottom, and then every once in a while we basically just cut it off, and the seaweed sinks to the bottom of the ocean, and then it regrows. It's kind of like hairs that regrow. That's the cool thing with seaweed. It can just keep growing, and if you fragment it, it just keeps growing back. So if you have two parts, then they will both grow and continue growing. So we call it, they regularly get a haircut, and then it regrows. So to give you an idea for the scale, so the idea is then if we grow seaweed on 0.1% of the oceans, it could remove a gigaton of carbon from the atmosphere, which is quite a lot. It's 2% of human emissions, but it's still 1 billion tons of CO2 per year. And that's how it would look like. You have a fleet of these farms swirling all around in the ocean where there's good nutrients. And then the robotics problem comes in because there's certain areas which have higher nutrient densities than others. This is in the background now, nitrate, but you also need phosphate and other ones. You also want to avoid certain areas, for example, chip channels and marine protected zones. And lastly, for actually cutting off the seaweed, you want to be not in the shallow oceans, because then the seaweed is not out of the atmosphere for very long, but you want to be in the deep ocean trenches, ideally. Think about Mariana Trench, stuff that is as deep as possible you can get it. So that's basically our robotics problem. And I'll see there's like something in the chat. I'll answer in 1 second. Let me just like finish that arc. The challenge now is like, that's our robotics problem. That's what we want to do. The challenge is that navigating stuff on the open ocean, typically we do it with like big ship engines, like cruise ships. But that's too expensive to do it with this classic ship control methods, which are overactivated. And that simple reason is because the power you need to push things around, because of drag force, scales cubically with your velocity through the water. And as you can think about these seaweed farms, like they're kind of like a house below the water, very little on top, but most of it is below the water. And pushing that around actually has huge drag forces. And that's kind of what makes this challenging. And those drag forces, because of the reference area and the non-ergonomic coefficients here.
Can't hear you.
Velocity.
We couldn't hear you.
We couldn't. Oh, like in general or just now?
I can hear you fine.
It's okay now, but it went away for a minute.
Oh, okay.
We can hear you, Marius. It's okay.
Yeah, I think I'll. Okay. Was anything? Is the problem statement clear right now? Why we can't use like classic overactivated steering? Otherwise, I'll go back and yeah, repeat that.
I think it's okay.
Okay.
Yep.
Thank you. Oh, one question was, it can also be used for food, as a source for food. Like, why would you want to sink it? That is the totally valid point. Like the seaweed can also be used for biofuels, for feeding it to cows, it reduces methane emission. It has many other use cases. And that's why also the nearshore seaweed farming is basically like having increasing demand. We just engineer our, like the startup Ficos is basically aiming for the maximum carbon impact possible. And that's why they go for open ocean seaweed farming. So this solution is specifically engineered for open ocean farming, which lends itself very naturally to carbon removal. But you could also steer the farm somewhere close by, do the harvesting, use the seaweed biomass for something else. So the methods we develop can be used for both. Okay, so the challenge is, this is our robotics problem. We want to maximize growth. We want to avoid certain areas and be in other areas when we have like at the peak of our growth. But it's too expensive to do it with classic ship control because of the drag forces. So the idea we started with is the oceans is full of powerful currents. So the idea is, can we actually navigate our robots by hitchhiking on these ocean currents? Turtles use the currents as well. So why can we use a similar effect there? And to illustrate it a bit, we have like our little farms, which have very small underpowered motor, 0.1 meter per second. If we can do that, then because of the scaling law, this cubic scaling law, we need 1,000 times less energy compared to classic approaches operating with 1 meter per second. And needing less power, or in this case, actually, this should be power. Needing less power means you need a smaller motor, smaller batteries, smaller solar panels, which then means the floating farms get a lot cheaper, which then enables cheap ocean autonomy by operating in this kind of fashion. And here's an example of how that looks like. We have a little farm, 0.1 meter per second maximum activation, and we're operating that over 40 days. This is the Gulf of Mexico, and we want to go from the red starting point to the green target area. So if we just passively float, no activation whatsoever, we just like keep in this eddy, float around a bit, and then get drifted to the right, left. Now, if we have a naive approach, basically just like always activate towards the target, very simple control approach, we like still take one round in the eddy, and then we like can escape it a bit and we make some progress. But if we have actually the ability to like use the currents for our advantage, then this is how we get towards the target. And this is like how it looks like in an animated fashion. And the idea is that the farm can ride on beneficial ocean currents, and it uses its small propulsion, like here, indicated by the arrow, strategically to change these eddies, like here when it goes from one eddy to the next, to make sure that it actually goes out there and changes them. So that's basically what we want to do. And now I'm going to go into the problem statement a bit, and then basically how we solve that and how we make that possible in realistic conditions. So problem statement, we start very simple. We just have XY condition, like XY coordinates for our seaweed farm. Our objective is we want to find a policy that maximizes some kind of the expectation of some kind of objectives. It could be like navigation, get towards the target as fast as you can. It might be maximizing seaweed growth. And we're going to do both later on. And the expectation is taken over, in this case, like missions, which is basically just like starting points. anywhere on the ocean. And the stochasticity comes from the different currents we might experience in that area. So that's basically the objective. The constraints is our dynamics. We model it with basically a actuation term. We now model it as holonomic actuation. And then we have the currents that are nonlinear time varying, basically pushing us around. And that's the effect we want to exploit, and they're also uncertain. And we have the limited actuation. The challenges now, there's like 3 core challenges. One, in realistic scenarios, you only have coarse forecasts of the flows available. And these are also deterministic. You don't get an ensemble of forecasts. You don't have an idea of the stochasticity, the uncertainty of your forecast, but you just get like, this will be the future forecast. That's what the providers, essentially the operational models, provide you with. Then you also have large forecast errors. They're typically on the order of magnitude of 0.2 meter per second. Our actuation itself is like 0.1 meter per second. So the errors are double as much as our actuation itself. And the third challenge is that we are under-actuated, which means, yeah, basically the currents around us are 5 to, like, in this case, like 20 times, but 10 times stronger is about the average. So we really need to rely on the currents to get where we want to go. And in this talk, basically, I'll try to see how we tackle it in 3 parts. One is realistic operations. We look at the questions like, how can we actually simulate realistic operations at the vessels in the ocean? That's what we need to validate our performance. And second, we're going to look at the core question, how can we strategically use the limited propulsion to achieve our objectives? And lastly, we look at how to handle constraints, specifically how to ensure safe operations to not get stranded on some islands, for example, but then also looking at how can we operate multiple farms as a fleet altogether and have some synergies to go with that. And I'm going to go over the parts. Basically, I give you the highlights and the ideas behind them, and we can go into details for each of the papers that are behind those ideas later on. So let's start with realistic simulation. This is kind of like a forecast that you get. This is kind of how it looks like. And we typically get 5 to 10 day forecasts, depending which system you use, the US or the European system. And what we did is basically build a closed loop simulator that basically provides the controller daily with new forecasts as they become available. And then you have true currents that are different than your forecasted currents by the forecast error. And the system simulation basically runs on those true currents. And then you basically have a closed loop control loop where the control gets feeded to the true currents simulation, and then you get feed the state back, so you have state feedback. And the simulator we build is like fast and both modular, so we can use like analytical currents, we can use currents from different forecast systems. And the key thing now to make it realistic is the forecast error. So the question is, how do we make sure that this forecast error is realistic of what a vessel will experience in the open ocean? And you can think about a forecast error looking kind of like this. It's basically a huge error field of a 4D matrix. You can think about it as a video. And basically, how do we ground this forecast error? And what we have available is point-wide measurement by drifter buoys. You have a couple of 100 buoys floating around in the open ocean. And they're always measuring like the currents at their specific positions. So we have point-wise measurement of the forecast error available. So we have some statistics that we can use. And we found 2 ways to like have a realistic forecast error. One is we basically just use different ocean model providers. We use like Copernicus, the European system, for the forecasts, and HICOM for simulating ground truth currents. And what we found, actually, if you like compare the difference, like the forecast error on both of them, it's on the order of magnitude of the forecast error that you can get from the statistics from those floater buoys. That's one way we did it. And the second way is, can we train a generative model and tune it on this sparse drifter data? And we have 2 variations of that. One is like more using geostatistic and simplex noise, like having a strong prior. And then one we basically experiment around with GANs to like have more high capacity models. And the idea is it always basically, given on the forecast, it spits you out a noise sample. And what we found there is that basically with this amount of data, GANs don't really work. So you basically need a very strong prior. And that's where we use it in the end. We use the geostatistics method with a strong prior for doing that. Okay, so now we basically have, how do we simulate these realistic currents? You have this closed loop simulator. Now we're going to go towards how can we achieve our objectives with that limited propulsion we have available. And here's a sketch of the control pipeline, just to have an idea how it looks like. You first get some inputs, which could be like weather conditions, maps, ship channels, stuff like that. If it gets feed into a planner and you want to do as much as computation as you can in the cloud, because the contact you have with the Seaweed farm is only via satellite connection, and everything you send over here is like very expensive. And then you have the local planner that takes some compression of the global plan and basically does like its local actuation, and also has available the two sensors, which can be like sent back to the planner, but it also can be used directly to adapting the plans as you go around. And the questions we're going to answer to like get to this under-actuated control problem is, first, how can we navigate with known flows? Once we have an idea about that, we can look at how can we handle the flow uncertainty, because the flows are not known. And lastly, how can we maximize seaweed biomass over months, so long periods of time, when the forecast itself is only 5 to 10 days long, but our objective is like actually over very long periods of time. So this is how we're going to approach this. So let's say for now the two currents are known. It's still a hard planning problem because the dynamics are nonlinear and time varying, and we're under-actuated. So one thing we tried in first was like, let's just like use nonlinear programming, form it as an optimization problem, and try to, basically solve it. The problem is there you don't have any optimality guarantee. You get stuck in local minima, and it basically has like a lot of discretization issues because you need to discretize in space and time. Or there's variations to get around it. Similar issue with evolutionary algorithms, graph-based algorithms. Some of them have like optimality guarantees, like time-varying Dijkstra, but you're still like discretizing heavily. And the one that we found basically both gives you guaranteed optimality and the known flows, and discretizes only at the last point when it's needed, is dynamic programming. And that's what we're going to use. And we do that in continuous space. I'm not going to go now into like the full details how it works, but I give you like the sketch of it. We use something which is called reachability, and we have a certain variation of it, which we call multi-time. Actually, should like stop that here again. What we call multi-time Hamilton-Jacobi reachability. And what it is basically, this is our target region. This is our starting point. And we have a value function which embeds how fast can you get towards the target. And the outside area of this is the reachability. And we calculate it backwards in time, as you do with dynamic programming. And what you get there is the backwards reachable tube. So it tells you for each time, these are all the points from which there exists a control trajectory such that you can reach the target in a specific amount of time. So just at the edge, like around here, it takes you, the fastest control trajectory gets you 116 hours or 120 hours to get towards the target. If you're close to here, the darker blue, like you get towards the target faster. So that's basically we developed the method, slightly like variation of Hamilton-Jacobi reachability to like do that. And the cool thing, what it does, it gives us this backwards reachable tube for all times. So we can calculate backwards in time. And also gives us the optimal control. And the optimal control in this case is basically just like the gradient. So you just activate the gradient of the value function, gives you the time optimal control to get towards the target as fast as possible. And then you can basically like compute it forward, which then gives you the time optimal trajectory to reach the target and exactly how you need to activate. And the other cool thing which this allows us to do is basically, if you're in the reachable set, it gives you the time optimal control. If you're outside of the reachable set, so it's impossible to reach the target, it gives you, get me as close as possible towards the target at the final time. So it has some kind of like element of graceful degradation, if you want to call it like that. Whereas like if you use nonlinear programming, you'll just tell you infeasible. And that's, I think, an important element which we're going to use later on as well. So now the question is, how can we handle flow uncertainty? If we have a distribution, we can do some like expectations and like some risk weighting and doing like reasoning over that. But for now, we don't have any flow distribution available. So what can we do? One thing is just plan and forecast, use open loop control. As many of you probably tried, something like that fails miserably because the reality is different and there's errors that just accumulate. Another thing we tried is plan on the forecast and use waypoint tracking, like just trajectory following, waypoint tracking, which works very well if you're overactivated. But in this case, it actually fails also badly because it wastes energy sticking to a plan that's not longer feasible anymore and trying to like get towards that plan trajectory, even though that's not useful anymore. Another one is like we can get an error bound and use robust control. Give me the control that despite the worst case error, gets me towards the target. The problem is that the errors are very huge, like in our case, realistically. So if we assume a realistic bound of 0.2 meters per second, then there just is not a robust control that exists that gets you towards the target. because the arrows is stronger than us ourselves. So what we found, the only thing that we found which is well applicable then is, let's use the idea behind model predictive control. Let's just replan frequently from our new position, and anticipating that if we plan frequently enough, even though our model is not so great, we might still get towards the goal. And the key insight then is that the value function already contains the optimal control for all states and times. And if we just apply that closed loop, if we get this gradient from it, closed loop, this is equivalent to full time horizon replanning at every step. And I'll show you how that looks like in our framework. So we have these 5-day forecasts, and daily we basically calculate these time to reach maps. That's the value function we use to get from dynamic programming. And then basically we just closed loop apply, always do this gradient calculation. And the cool thing, if you compare it, for example, to normal MPC, is we get full time horizon replanning. So you're not limited to a short time horizon in the future. It's very low online compute. Once you have the value function, which you compute once per day, it's a bit of compute. But online, it's like, very low, second, maybe 10 milliseconds kind of range, because it's just a gradient calculation at the current location you're at. And it has this graceful degradation feature that even if you're outside, it doesn't give you infeasible, but just tries to get you as close as possible to the target. And here's an example of like more animated, how that looks like. You get your forecast, you calculate your time to reach map. Again, red dot here is where we start. This is where we want to go. So we calculate it backwards in time. This is the optimal control if the currents are accurate. And now what you're going to see is that this plan will change at every time step. And at some point, like over here, it realized, okay, this plan is not feasible anymore. So I guess it's just going to go the other way around. I'll replay that again to make sure that's visible. Yeah, that's basically this idea of replanning at every time step. And then next forecast comes in, you can do this replanning from this new position with the time to reach maps. This is your planned path, but then it's going to deviate slightly from it, and it's going to replan the path at every time step. And next forecasts come in, number 3, okay. But at some point you reach the target, essentially, if you just follow that over and over again. So now for our experiment results, like let's look at how that actually performs if we run a lot of simulations. And what we do there is we have our farm, 0.1 per second, and we do it over 6 days, because that's like how the forecasts are long, essentially. And this is our missions that we sample. We sample a large set of missions distributed over time and space to make it representative. And what we do is we have this made of success rate. It's a very crude metric, but that's kind of like we wanted to choose it for, are you able to reach the target? It's basically binary. Like if you reach the target, it's success. If not, then you basically fail. You'd have a timeout kind of. And the first thing we found, which was actually very curious, that naive to target performs surprisingly well. It's like 78% of the time it like naive to target, just the baseline reaches the goal. And then we compare it against with this planning, getting the optimal control on the forecast, and then using waypoint tracking, which actually performs worse because it sticks to this plan. We also compared it to a robust control version with unrealistic low forecast error. And then our replanning approach, multi-time HJ reachability, and applying it closed loop, which gets the best performance of 82.3%. And to give you a bit of intuition, like why that naive to target, why the baseline is so good, the reason is because we sampled missions that are fundamentally feasible. And over short periods of time, if it's feasible, like then you're mostly likely going to drift towards the target anyway. So if you increase the time horizon from 6 days to 30 days, this success rate drops a lot. Naive to target basically gets down to like 20%. So it's basically the reason why this is so good is because the time horizons are very short, you're under-actuated. So most missions that you sample that are actually even fundamentally feasible given the true currents are not too crazy complex in terms of taking many bifurcations and eddies. And it gets a lot more complex for longer periods of time. Okay, so this is one way of handling this forecast uncertainty that we found works quite well. A second one that this group is probably quite familiar with is, can we use data assimilation to improve that? And the idea is that we can learn about the currents online. Basically, we know that at where we are right now, how we're drifting around, if you compare past GPS position, actually gives us a measurement of the currents at this position. And we also have them about the past. So the idea is, can we use those measured currents to improve our local estimates or the estimate of the local currents? So instead of having this diagram, now we have something in between, which is basically a data assimilation approach. And the idea is we only like do data assimilation locally because, yeah, the measurements we have will not tell us something about like currents very far away, or not very much at least. And the way we did that, or like one approach that we like did for that for the master thesis of a student I worked with, is we take those measurements, like a trajectory measurements, we then fit a Gaussian process towards it, a 3D Gaussian process in like space and time, 4D actually. And then we also take the forecast, feed it into a 3D UNet, and then train it in a supervised learning manner on improved forecasts. And what we find is that it can reduce the forecast error locally by up to like 41%, depending on how much area you choose around it. And this is for 12 hours, so very like localized in time and also in space around the platform. And yeah, basically this is I think a very big potential to improve also the navigation performance, but it hasn't translated to that yet. We have like still have to run more experiments to like investigate why. Another approach we did, and I'm going to go through that very fast, is basically reinforcement learning. Can we learn a policy that hedges against the uncertainty if we just let it train in our simulator long enough? And what we do there is we feed in the value function because it also has a lot of compressed information about the forecast instead of feeding in this huge 4D matrix. And then we also feed in the measured currents as a Gaussian process, and then it should predict an action. And we see a small improvement of like 1% success rate over our HJ closed loop approach in this case. And the last thing we're currently working on, but we don't have like good results yet and realistic currents, is actually what if we have a distribution? Then we can do data assimilation, but we can do it actually maintaining this distribution. And not the operational forecast system, they don't have forecast ensembles, but like experimental ones that researchers are working with, they can produce ensembles, which is basically just like you have different versions, let's say 100 different ensembles, and it gives you 100 versions of how the future might look like. And one thing you can do is basically filtering. You get a measurement. In the beginning, you like have all these 100 futures, or most are equally likely. If I get a few measurements, maybe 90% of them are not likely anymore, but like 10 of them are the most likely, so I'll just plan on those. And then you just do filtering, and then stochastic control, filtering, stochastic control. Another one is using partially observable Markov decision processes, which also has this element of information gathering to make sure that you narrow down and forecast as much as possible while still maximizing your objective. And we have encouraging results for that in analytical flows, but not in realistic flows yet. Because then you need to like do a lot of like dimensionality reduction to make it feasible to run these algorithms. Well, now this is a summary for now. We basically talked about navigation as a control objective and how to handle uncertainty. And what you actually care about is not navigating, but we care about seaweed growth. So now we're going to look at maximizing the seaweed growth and reasoning beyond the forecast horizon, because seaweed grows typically over a period of 2 to 3 months. And this is work with my student Matthias. And the idea there is we extend essentially the state space by a third variable, which is seaweed mass. And we model it as like some kind of exponential growth factor. And we have a realistic model. We get like some nutrient data for that. We basically just model the exponential part of that sigmoid. And as you can see, depending on the nutrient conditions and temperature, you can grow up to 14% per day. That's kind of what this map shows us. And this is also a time-varying map. It's just a snapshot. Now, the challenge is that the growth is over a month, but we only have 5 days forecast available. So how we tackle that is in multiple steps. Oh, now it's lagging a bit. Okay. So let's look at first for like 30 days. And if we start here at this green dot and we just let it drift for 30 days, just like as a baseline, then what we get, we start with 100 kilogram seaweed mass, and we drift in a region that actually has negative growth because there's some respiration factors. So yeah, not so great. What we first develop is then we develop an algorithm to maximize seaweed growth with known flows using, again, dynamic programming and formulate as a continuous time dynamic programming and deriving the HJ equations. And what we get there is that actually over 30 days, this will be the optimal path to take if you know the true currents. So you basically first go through a path of like low currents, low growth, and then you get to this like area down here, which has good growth conditions. And then we can use the same method actually from above. We just basically get the feedbacks policy based on these daily forecasts, which again is just the gradient of our value function. So very similar to before, that's how we handle the uncertainty. That's how we get a feedback policy. But the problem is now we only have 5-day greedy policy because we only have 5 days forecast available. And if we apply that repeatedly, what happens is it goes to like this close by good growth region because it only reasons over the next 5 days. But then it doesn't realize that the currents over here are actually so strong that you're going to be pushed out over those 30 days. And you get pushed out of the good growth region and eventually also out of our region. That's why our simulation stops here. So what we want is basically reasoning beyond the forecast horizon. And what we do there is we extend our value function by estimating the expected growth after the forecast. And we use that by using seasonal averages. We just look at what are the currents last year, January, on average, and I just use those. Use the growth map from that time as well, and then it gives us an estimate of the expected growth if you end up in a certain position. And we can combine it to then have a function that gives you like optimizes over this long period of time. What we find then, if we apply that sequentially, always replanning on the new forecast, is that we get very close towards the global optima. It also finds this path towards the more global optimum down there. And lastly, what we do is we introduce like a discounting factor to mitigate uncertainty, just because the future currents are then less likely or like less sure that they will actually be the way that you anticipate them to be. So we just have a discount factor there as well in the dynamic programming. And this is our empirical results for that. We do like, again, 0.1 meter per second, 30 days. And we basically show as normalized growth. If we have the known currents, so basically the optimal growth we can achieve, and we sample again a huge set of start position in this case, over 1 year. And basically known currents is just 100% relative growth. If you just do passive floating, it's 88.2%, also surprisingly high. And the reason is because you don't get actually, those regions are fairly homogeneous. So like the way you start actually makes a big difference. So you get like 88.2% if you just passively float. If you do 5-day greedy, that increases already to 559% of the best possible growth. And then if we use forecasted, average currents, and discounting, we get to 95.77%. And what is interesting is that the difference between 5-day greedy and long-term was smaller than we expected. And I think one reason why we think is that mostly the growth regions are fairly continuous. So there's less local minima than we thought. And a similar thing happens here, that if you increase the time horizon from 30 days to like 60 days, that gap increases. So that's that. And the cool thing, what we can do for that as well, we can use it for optimizing the farm design. So we can say, for example, if we have 0.2 meter per second, how much more growth can we get? So we can like kind of use this algorithm to like also estimate, like basically help them in the startup FICOs we work with to basically optimize their farm design. So now we talked about the second part, and now we're going to go to handling constraints. So on the open ocean, like there's two constraints we think about. One is like safety, the other one is multiple farms. And for safety, which is the work with together with Andreas Döring, is what does actually safety mean for under-actuated vessels? We identified multiple risks. We identified stranding. This is like some stranding study we did around the Hawaiian Islands. Like what's the likelihood that you're going to strand in 10 days around those islands? And you can see if you're close to the islands, then the risk of just getting stranded is quite high. There's collisions with ships, and there's like garbage patches that your motor can get entangled with. So that's the risk we look at. And the idea is basically that we just include time-varying obstacles or potentially time-varying obstacles in our dynamic programming formulation. So this is like, again, our time to reach map, this time for navigation. It equally applies to seaweed growth. But the idea there is that instead of like just applying it without obstacles, we actually just include those obstacles in the dynamic programming formulation using, in this case, bathymetry, like depth maps. And then we can see that basically that's where the controller is trying to avoid it, or is avoiding those areas. And again, we do the same procedure as above. We plan on the forecast with those obstacles now, and we apply it closed loop. And that reduces the 10-day stranding rate from 5% before in our empirical experiments to below 1%. It can't fully eliminate it. And this was also high-risk region. This was like not on the open ocean. We only looked at regions like where it's close towards the shore, just to make that clear, because otherwise 5% is quite high. And the last thing we looked at, or almost last, is is that we have, how can we operate multiple farms? Let's say we have not one farm, but we have like n farms. And this is like an example how they just hang out. And what we want is basically we have an objective. The cool thing is that in our case for seaweed growth, even for navigation as well, those objectives are essentially just the sum of the individual objectives. Like the growth of different farms are not coupled dependent of each other. She nicely decomposes in the individual objectives. And the cool thing is the value function already contains the control for all farms. So we just need to compute one times this dynamic programming thing, get the gradients from them, and then we already have the optimal control for each of those farms. So that's quite neat and basically reduces the computation cost for control by quite a bit. So that's the starting point we're at. But this control that we get from that doesn't consider interactions between the farms. Like here, for example, in this case, basically tells you, hey, if you want to navigate towards here, this is kind of how you should like actuate. But then those farms don't know about each other, so they might actually actuate towards each other and collide and get entangled with each other. So our optimization problem is optimize the objectives, which is some of individual objectives, such that you don't have collisions between the farms and you stay connected. And what we mean with that is that they can communicate with each other in a local mesh network, so that instead of each of them having a satellite modem, maybe just one of them needs it, which reduces the cost again by quite a bit. And locally, they communicate with each other with local radio stations, which then reduces communication cost. And they can also share information about each other for nutrients and currents. So basically get also better in data assimilation because they have the estimates of all the currents around themselves from the other farms as well. So the idea is, can we reuse our single agent controllers while ensuring safe interaction? That's the basis for it, the starting point for this work. And the way we approach it is we take our existing controller as a performance controller. It just looks at performance. Then we also develop a safety controller, which is inspired by the potential function approach, which essentially just says, hey, you want to basically try to be at an optimal distance, which is like the half of the communication distance. And if you get too close, then just like go away from each other. So you should actuate just like these two, like actuate fully away from each other. And if you're, for example, far from each other, like at a risk of losing the connectivity, you should actuate towards each other, like you can see in this kind of, between these kind of farms here. We use a potential function to do that. And then we combine those two approaches by having what we call low interference, safe interaction controller that just takes the scale performance of the controller, of the performance controller, and the safety controller. And what it does is basically trades these off. So they all, like basically it's a factor between 0 and 1. If there's a high risk of collision, like down here, then you basically want to ignore the performance controller and just care about safety. But if like basically both of them are like in a good distance towards each other, no risk of losing communication, no risk of collisions, you basically just take the performance controller, which is what happens for 1 and 3. So this is what the spectrum of interactions you see. There's low interference, like basically mostly you just care about performance in this case because you're good distances. There's maintained connectivity because this one has the risk of losing connectivity, so they try to like move towards each other. And then there's avoiding collisions if they're like very close to each other and there's a risk of colliding, then you also just care about safety and ignore performance. And again, with that, we prove basically that under certain conditions on the currents, we can prove that this will maintain safety. And yeah, we did also some empirical experiments. If we don't have our interaction controller, basically just everybody follows performance controller, then we have quite a lot of collisions and a lot of disconnections happening. And we can reduce that with our approach, which we call like a closed loop fallacy, LISIC, low interference safe interaction controller. We can reduce that by quite a lot. It still happens sometimes because that's a challenging aspect of this, this kind of like environment we operate in, but we reduce it by quite a lot. And with that, basically this concludes the theoretical pieces of this work as well, and like the different papers that this summarizes. And what I want to just highlight a bit is that it's not just work in simulation, but we're actually working with FICAs to test it on the real ocean. And this is like our prototype for navigation testing, no seaweed on the bottom yet, which we work with in San Francisco Bay Area. There's like some drag tests we did at the Berkeley pool. And this is when we send it out and we have like some short missions. We first start with 1-day missions just to see if it survives, satellite connection, everything. So this, are excited to see how generalized, like how approach actually works in the real world. And summarizingly, we basically went from this idea of like having seaweed farms. It's too expensive if we have like strong overactivated control. the idea was leveraging the ocean currents and thereby reducing the energy you need and the power you need by a lot to then enable affordable and scalable carbon removal. And what we have is developed these algorithms in simulation for safe operations of fleet of low-powered agents hitchhiking ocean currents. And this can be, one application is seaweed farms. That's where we started with inspiration, but it can also be used for active drifters. So the buoys could like search areas to like minimize, basically like to optimize the information they get from it. It can also be used for an approach that people are suggesting for decarbonizing transportation in the oceans, like shipping vessels, by having floating solar farms that just like basically sit in the middle of the ocean, store their energy in synthetic fuels, and then tankers come by to pick them up. Potentially also be used for what was Project Loon at Google, like beaming internet to rural areas using like stratospheric winds. So you can use it also in other flows, not only just currents in the ocean, but also like winds. And with that, I just want to acknowledge my advisors, the collaborators at FICOS, and my master students I work with, and yeah, open it up to questions from you guys. Looking forward to the discussion with you.
Thank you, Marius. That was a very thorough introduction to everything you've done recently, I guess. Yeah, so you have any questions for Marius, just leave them in the chat, or you can raise your hand and yeah, you can unmute yourself. I think Filippo, let me...
Hi, Marius. Can you hear me?
Yeah,
Yes,
I can.
Great. First of all, thank you very much for the talk. It's mind-blowing the fact that you can literally navigate the whole ocean just by using the currents. It's really, really cool. I have a couple of questions. I don't want to take too much time, but first of all, I also know that there is a technology which is called permaculture to both preserve biodiversity and perform carbon drawdown, as you were explaining. Have you guys also explored joining the forces with that technology?
Permaculture, like the version of iPermaculture that I'm aware of, is it's basically on land that you like try to like intermix different plants together so they basically like help each other like kill weeds and those kind of things. Is that what you mean?
No, I think what I mean is there are like studies of growing seaweed outside the ocean, but not only for carbon drawdown, but also for simulating upwellings, ocean upwellings, and so restoring biodiversity.
Okay. So for our specific case, we didn't look into that because the team is essentially at FICOS, they're aiming it to like, we want to draw down as much CO2 as we can, and that's why we engineered for carbon removal. But there's a few organizations that are looking actually into that. I'm blanking on the name. There's an Australian guy. Yeah, I think that might be the one you like refer to, like ocean permaculture. He calls it ocean permaculture, which then like pairs seaweed growing seaweed and like mussels and other like, other marine animals together. And I think that is great, and we should definitely go ahead with that. And it's just a different application. I think it's just like a different angle to take it. And I think that's great for replacing work, for example, from fisheries and maybe replenishing fisheries. This is just engineered more towards produce as much biomass as you can by using the open ocean.
Okay, sounds cool. And then another question that I have is, have you guys studied the effect that dumping all the seaweed to the ocean seabed could have? Like, I mean, if we want to remove 2 gigatons of CO2 by 2050, that would mean a lot of seaweed dumped in the ocean seabed.
Yeah, that's a good question. And we actually looked at that quite thoroughly. Not that we did our own research because we're not oceanographers. And I'm talking here for like me and FICOS essentially. I'm like working with them. And we talked to like many oceanographers about that. And the take they have is that it's a process that naturally happens anyway. Like there's biomass that reaches the deep ocean. And there's 2 things which happen to the biomass down there. One is like some microbes eat it, and basically that's like the nutrients they get. And then like CO2 gets released again, and like you have like basically the minerals get released again as well. Another part of it will be covered by sediment and then incorporated in the sediment, and then at some millions of years it's going to be oil again with high pressure and biomass being compressed essentially and can't decompose down there. So both these effects happen. We know that, or the oceanographers know that essentially. And the proportion of what happens, how much depends on where you like put it. In the certain areas, the deeper you go, the more likely it is that it gets covered by sediment, especially if you have ocean canyons, which have like sometimes landslides and stuff like that. So that's why we're basically working with them. There's an NGO we called Ocean Visions we work with, and they're currently developing a map where it's like good to like put it down. So that's one area to optimize for that. And the other one is basically that what oceanographers also say is like, well, the ocean is just super huge. And actually on that scale, like 70% of our planet is ocean. It's actually not that much biomass per area. It's like less than like a centimeter of biomass going down. So then the question is, do we just spread it out? Is that better? Or is it more like idea to like centralize it to like in a specific location? And we're working with like science agencies to figure it out. There's 2 current experiments running where they basically just took a bunch of seaweed, put it down to the bottom of the ocean and just observe what happens. So there's like still some science questions to be answered there. And we'll keep ourselves towards the best science we can to make sure we have the least unintended consequences that we can have. Yeah.
Okay. Thank you very much for the answers.
Welcome. Thanks for the questions and the interest.
Thank you, Filippo. Thank you, Marius. There's a question in the chat from Phil. He says, what happens to these currents driven masses when a hurricane is near?
Okay. So you basically mean like you're having this thing, this autonomous seaweed farm going around, and you have a hurricane going above you. That is a good question, and that's something we basically have to engineer those farms, or like the hardware of those farms has to be engineered to like be able to withstand that. One good advantage there is that in most of the, like in my sketch, it's not that visible, but basically on top of it, it's basically the size of like a work desk kind of thing. And below you have something that's 50 by 50 meters. So most of it is like kind of like below, and most of the winds happen luckily above. So most of it will be hopefully protected from like the strong effects there and like hopefully not get damaged, but that's something we definitely have to like engineer for and experiment with, and hopefully not operate in areas where hurricanes are very likely. Like the experiments we did was Gulf of Mexico, mostly because there's higher resolution ocean forecasts, but it's actually not the best area for us to operate because also the Gulf of Mexico is not necessarily that deep. So we're probably not going to operate in that area. Hopefully don't have that many hurricanes.
Thank you, Marius. Can I ask you a question in the meantime? So you get where do you get your information from the currents again? Sorry if I missed that.
There's two sources. One is the European forecast system, which is called Copernicus Marin.
Yeah.
And then there's like the American one called HICOM. That's our sources we use.
Oh, okay. Yeah, because I just remember in my PhD I used was it ocean current? No. Sorry, I forgot the name of the product, but because you can also estimate it from like Argo floats and things like that, right?
Mm-hmm. Yeah, exactly. So like so you mean the data from the drifter buoys, the global drifter program? Yeah. Copernicus has them as well, and they merge it together like these drifter program things. Are the one that also have the vertical profile, so they also dive down, I think.
Yeah.
Yeah. We use their like basically the API and like the data they had on Copernicus from that. Yeah.
All right, cool. It's kind of cool that you can use that data and then maybe now potentially you learn a solution and potentially give them that solution back for like automated drifters, like you said.
Yeah, I think so. I think it was like, yeah, it basically helps us to like estimate this like realistic forecast error model that we then use to train our model, like evaluate our experiments and then train our algorithms on. Yeah. But I think the other cool effect that you will have, I think, with this is if that is successful and it's something that gets deployed with like, then right now I think we have like about 1,000 drifter buoys in the ocean. Mm-hmm. But then if you have 100,000 farms, that basically equals like 100,000 more of those drifter buoys. So like you just get a lot more data, and the data gets produced anyway by the farms operating. So you basically can supply it back to the scientific community. That's always also what FICOS wants to do, basically, like, and hopefully thereby also helping increasing our information about the oceans, thereby increasing also like improving the forecasts again, and hopefully have a nice virtuous cycle there.
Cool. Yeah, and everything sounds really exciting. Just let me check if there are other questions. Oh yeah, Filippo, you're gonna go ahead.
Yeah, sorry, just if there's no other question. Just wanted to ask you, you mentioned at the beginning that you're also planning to do the haircut, to cut the seaweed.
Yeah.
Could you like expand a bit more on like how you're planning to use a robot to do that?
That one I cannot talk about. It's like basically a mechanical design thing that Vicos is working on. But basically the idea is like, yeah, basically you want to cut it in such a way that there's still something left so it can regrow and the rest sinks. Yeah. I cannot say more exactly how it works.
That's cool.
Thank you, Filippo. The other thing I was gonna ask you, like the main one thing I didn't understand, or was like a bit tricky for me, in your slides when you're showing how long is it gonna take for the drifter to reach a certain target, is it depends on where you drop it, or is where the maps of like if you drop in that point, it will take, let's say, 150 hours to reach that point? That's I wasn't.
It is. Let me go to that slide, and it makes it easier to explain. Zoom again. Here, okay. Share screen. Share screen again. That's. Where is it? Should be somewhere. Oh no, after realistic simulation. It's here. Yeah, this slide. So this value function tells you basically, like we compute it backwards in time, and then it tells you for each point how long do you, if the currents are accurate, and if you use the optimal control, this is how long you'll take to get towards the target. This is what this value function tells you. And then like one thing you can use it, or like people have used it in the past, is actually what you said is like, where should I drop my drifters? So if they do like experiments with drifters that they like put in to like do the data simulation kind of methods, like our oceanographers we work with at MIT, they have used this in the past to like design where they should drop their drifters. In our case, like the seaweed farm is just at a certain position, so we can't really like drop it anywhere and move it around. So it's just like it happens to be there, and we just get the gradient from it, and thereby the time optimal control or growth optimal control from it.
But in this case, the state of the ocean will change during those 120 hours, let's say. So that's the optimizer knows that this will change as well, right?
It knows the time varyingness. Like if you see like basically the it knows the time varyingness, but it still like assumes like this is basically the time varyingness, and you can see like how it moves backwards. It knows this time varyingness.
Okay.
But it doesn't know like that there's a forecast error. It still assumes that the forecast will be accurate.
Yeah. Okay.
So it basically has a nonlinear time varying currents in there, but like it assumes the forecast to be accurate, which is not the case. So you just plan on the best information you have, and then we plan frequently enough that you still get there, even though the forecast is not perfect.
Mm-hmm. And in terms of like, while you're working with global data sets, but I see like your case is more in like in the Gulf of Mexico, and then now you're testing your things in the Bay Area. Will your problem scale to other regions where like there might not be as good data as in like the Gulf of Mexico, for example, where we have like the US will have like that area quite well studied, but if we look to like Latin America or low income countries, for example, if you don't have like as rich data as you might find there, what?
Yeah. So the good thing is these global models, like from Copernicus and HICOM, they produce higher resolution forecasts for the areas of interest. So US produces higher resolution forecasts for Gulf of Mexico. The European model produces like for the Baltic Sea kind of area where it like produces good higher resolution. But both of them have global models, which are more coarse resolution of the forecast predicted. And I think the difference there, like going through a different region, basically is like just those current patterns are different, and then maybe your forecast area in those areas are higher, which then makes it more challenging, which then like basically the numbers I showed you in terms of the empirical results, they might change there a bit, but the method will still be applicable. Like you still have forecasts. Maybe now it's a bit more challenging because the current structures are more complex, and then you have like lower success rates and lower seaweed growth compared to the optimal. In some areas, maybe the currents are easier to predict and there's low forecast errors, so then those results will change with the region you're in, but the method is applicable in all of them because it just relies on forecasts and data available globally.
Yep.
And we'll see, like, that's, I think, the interesting thing we are evaluating with our, like, experiments in terms of, like, how is that actually gonna, like, how does that, the empirical results, how do they generalize to the real world conditions now? We start with San Francisco just because we're there, essentially, but eventually we want to go to, like, other regions.
Yeah, no, that's no, it sounds, everything sounds really, really cool. It really reminds me of what I was doing for my PhD as well. So that's good.
Yeah, we should do that.
I don't know if Phil, do you want to ask a question or? Sorry, you're muted, Phil.
No.
Yep, go ahead.
Okay, no. The question is there a way to, I'm going to say, take a barge and create a seed pod and then take that out someplace and inject it? Or are you going to wait for them to drift out there to be, how could you generate seed pods so that you have more active flow? Is my question, I guess. Okay.
Yeah. I think that we still have to figure it out. We don't know. I think the current idea that we're discussing with FICAs is you have like some production line, which basically just produces a lot of them. And then you basically launch them in the ocean, and then you have a boat that drags them out towards where they can catch the first currents in like maybe like groups of like 10, 20 of them. And then hopefully they stay together as like a fleet as we, for the algos we develop. I think that's the current idea. But
is there any way this could be used
probably
for
will
the
change once we learn more? And
is there any way this could be used for the dead zone of the Mississippi River? Do you know what the dead zone of? Do you know what the dead zone of the Mississippi River is?
I assume it's like that. You have. I know that there's like very high nutrients coming in.
Okay, when you go miles out into the Gulf of Mexico, there is no oxygen in the water. It's gone. There's the effluent of the Mississippi River is essentially oxygen starved. It's been destroyed by the chemicals and things that have been put in it. So is there any way that something like this could be used to improve the dead zone of the Mississippi River?
I think so, yes. And I know that like there's one project in France that there's a similar river kind of situation where you basically have like too high nutrients, you have like toxic algae blooms, which then lead to like this oxygen depletion areas. And they're basically having these seaweed farms just at the exit of that river to the ocean for basically filtering out those excess nutrients and basically revitalizing that water. So I think there's very early projects towards that. It's typically anchored farms because it's near shore enough that you can anchor them. And I think also, I'm not sure like how deep it's there, but I think a nearshore farm with you anchor it would make more sense for that.
Okay.
And
all right. Thank you.
There's potential for that. Yeah.
Thank you, Phil. I think we're gonna leave it to here, Marius. But I want to thank you again for sharing your time, your work with us. And I'm sure like if people want to connect with you after the talk, that'll be beneficial for everyone.
Yeah, happy to chat. Thank you very much for
no
your
worries.
attention and having me.
Thank you. Thank you everyone for attending the seminar as well. Have a nice week.
Bye.